What if I told you that right now, as you're sitting there, something in the universe is moving so fast it could circle the Earth 7 times in a single second? Speed isn't just about race cars or fighter jets out there in the cosmos. The laws of physics bend to accommodate velocities that would make even light seem sluggish by comparison. Picture a cosmic drag race where the competitors aren't machines but pulsars, black holes, and particles flung across galaxies at unimaginable rates. And here's the wildest part: the universe's speed champion isn't what you'd expect. It's not a shooting star or a rogue planet. It's something so bizarre, so utterly mind-bending, that it challenges everything we think we know about motion itself. Buckle up, because today we're taking a tour through the most extreme speed demons of the cosmos. Over the next 30 facts, we'll meet objects and phenomena that defy logic: neutron stars spinning hundreds of times per second, jets of plasma screaming out of black holes at nearly the speed of light, and even entire galaxies being hurled through space like cosmic cannonballs. And just when you think you've heard it all, we'll reveal the one thing in existence that holds the uncontested title of fastest object in the universe. Spoiler alert, it's not light. It's not even something made of matter as we know it. This champion is so strange, so counterintuitive, that it'll make you question whether the universe is playing by its own rules. But this isn't just a list of mind-blowing stats, it's a journey into the heart of what makes the cosmos tick. Speed isn't just a number out here, it's a force that shapes galaxies, bends time, and even rewrites the laws of reality itself. By the time we're done, you'll see the universe in a whole new way, as a place where the ordinary becomes extraordinary, where the impossible happens daily, and where the fastest things in existence are hiding secrets we're only beginning to uncover. So let's dive in. The starting line is right here. Let's kick things off with the universe's ultimate speed limit, the speed of light. Clocking in at an astonishing 299,792 kilometers per second, light doesn't just move fast, it defines fast. According to Einstein's theory of relativity, nothing with mass can ever reach this velocity, let alone surpass it. Think about that for a second. No rocket, no particle, no cosmic phenomenon can outpace a beam of light. It's like the universe has a built-in speed governor, and light is the unbreakable barrier. To grasp just how blistering this speed is, picture this. A photon of light could zip around Earth's equator 7.5 times before you even finish saying 1 Mississippi. It could reach the moon in just over 1 second, while a modern spacecraft would take days. And here's where it gets even wilder. Light speed isn't just a number, it's woven into the fabric of reality itself. Time slows down for objects approaching light speed, distances shrink, and the very concept of now becomes relative. That's why astronauts on the International Space Station age slightly slower than people on Earth. Their high-speed orbit literally bends time. But what makes light the undisputed king of velocity? The answer lies in the way space and time intertwine. As an object accelerates, its energy increases, but so does its resistance to going faster, like pushing a boulder uphill that keeps getting heavier. At light speed, the boulder becomes infinitely heavy, demanding infinite energy just to nudge it further. That's why even the most powerful particle accelerators, like the Large Hadron Collider, can only get protons to 99.9999% of light speed. The final fraction, it's like trying to fill a bottomless cup. Yet light itself pays no toll, it has no mass, so it doesn't fight against its own motion. It just goes. This cosmic speed limit isn't arbitrary, it's the backbone of causality itself. If something could outrun light, it could theoretically arrive before it left, breaking the chain of cause and effect. So while the universe is full of speed demons, none of them get to rewrite the rules. Light sits firmly at the top, the gold standard of velocity, reminding us that even in the vastness of space, some lines can never be crossed. Now imagine a star, not just any star, but one hurled out of its galaxy like a cosmic slingshot projectile, racing through the void at over 1,000 kilometers per second. These aren't theoretical anomalies, they're hypervelocity stars, celestial rebels kicked out of their galactic homes by the ultimate bullies, supermassive black holes. Picture a binary star system, two stars orbiting each other, wandering too close to a galaxy's central black hole. The immense gravity tears them apart, with one star captured while the other is violently ejected, flung into intergalactic space at speeds that defy belief. Take US 708, the fastest known hypervelocity star, clocked at an insane 1,200 kilometers per second. At that speed, it could travel from Earth to the Moon in just under 6 minutes, a journey that took Apollo astronauts 3 days. Unlike most hypervelocity stars, which are flung out by our Milky Way's black hole, US 708 seems to have been catapulted by a different mechanism, possibly a supernova explosion acting like a cosmic catapult. This star isn't just moving fast, it's escaping our galaxy entirely, destined to drift alone through the darkness between galaxies. The forces behind these stellar speedsters are almost incomprehensible. To eject a star at such velocities requires energy equivalent to a supernova's shockwave concentrated into a single, precise kick, and the aftermath is just as staggering. A hypervelocity star doesn't just leave its galaxy behind, it becomes a rogue traveler, untethered from any cosmic neighborhood, blazing a trail through regions of space where stars are few and far between. Over millions of years, these outcasts will cool and fade, becoming ghostly reminders of the violent physics that shaped their fate. What's truly mind-bending is that hypervelocity stars aren't rare oddities, they're part of the universe's grand recycling system. As they're ejected, they carry heavy elements forged in their cores across intergalactic space, seeding future generations of stars and planets far from their birthplace. So while US 708 might seem like a cosmic anomaly, it's actually a vital piece of the puzzle, proof that even at these unimaginable speeds, the universe is always working on something far bigger than we can see. But if you thought hypervelocity stars were fast, wait until you meet the universe's natural particle accelerators, pulsars. These aren't your average stars, they're the dense, spinning corpses of massive stars that went supernova, packing more mass than our sun into a sphere no wider than a city. And here's where physics gets wild. Some of these cosmic zombies rotate hundreds of times per second, flinging jets of radiation and particles outward at nearly the speed of light. Imagine a skater pulling their arms in to spin faster. Now replace the skater with a stellar remnant so dense a teaspoon of it would weigh 1 billion tons, and you've got a pulsar's terrifying rotational speed. Take the Crab Pulsar, the beating heart of the Crab Nebula. Born from a supernova observed on Earth in the year 1054, this neutron star spins 30 times every second, and its twin jets, twin beams of charged particles, race outward at over half the speed of light. These jets aren't just fast, they're unnervingly precise, sweeping across space like a lighthouse beam with such regularity that astronomers use them as cosmic clocks. The Crab Pulsar's rotation is so stable, it rivals the accuracy of atomic clocks on Earth. And yet, despite this precision, the forces at play here are anything but gentle. The magnetic field around a pulsar is 1 trillion times stronger than Earth's, ripping electrons from its surface and accelerating them to velocities where relativity starts bending the rules. What's truly astonishing is how these jets form. As the pulsar spins, its magnetic field whips charged particles around like a cosmic slingshot, funneling them into narrow beams at the poles. The energy released is staggering, equivalent to thousands of nuclear explosions every second. And because pulsars don't just sit still, their jets carve intricate spirals through surrounding gas and dust, leaving glowing trails that stretch light years across space. The Crab Nebula's eerie glow, that's the pulsar's high-speed jets slamming into debris from the original supernova, lighting up the wreckage like a high-speed collision in slow motion. Yet pulsars aren't just cosmic curiosities, they're laboratories for extreme physics. Their jets challenge our understanding of how matter behaves under conditions we could never recreate on Earth. At these speeds, particles don't just move, they're reshaped by relativity, their mass increasing as they approach light speed. And when jets from multiple pulsars collide, they create shock waves that ripple through galaxies, seeding space with heavy elements and high-energy radiation. So while the Crab pulsar might seem like a distant oddity, it's actually a reminder of how the universe turns chaos into clockwork, and how even in death, stars keep racing against the limits of reality itself. Now let's zoom in on the universe's most powerful particle accelerators, Blazars. These aren't just fast objects, they're entire supermassive black holes acting like cosmic railguns, firing jets of plasma so intense they outshine entire galaxies. At the heart of every blazar lies a black hole with millions or even billions of times the mass of our Sun, spinning at unimaginable speeds and warping space-time around it. But here's where it gets wild. Instead of just devouring everything nearby, these black holes channel some of that energy into twin jets of superheated plasma, launching them into the void at 99.9% the speed of light. That's not just fast, it's the edge of what physics allows. Take Markarian 501, a blazar 730 million light-years away. Its jets are so bright, they drown out the light of its host galaxy, pulsing with energy equivalent to 1 trillion suns. What's fueling this cosmic fireworks show? As matter spirals toward the black hole, friction heats it to billions of degrees, turning it into a swirling soup of charged particles. But instead of falling in, some of this plasma gets caught in the black hole's magnetic field and shot outward along its poles like a cosmic fire hose. The result, a beam of energy so focused it stays narrow for thousands of light years, punching through intergalactic space like a laser through fog. What makes blazars truly special is their orientation. Unlike other active galaxies, we're looking almost directly down the barrel of one of these jets. That's why they appear so blindingly bright. We're getting a head-on view of the universe's fastest particle beam. The particles in these jets don't just move fast, they're surfing shockwaves within the jet itself, gaining energy until they're moving so close to light speed that time dilation kicks in. From our perspective, the particles appear to move faster than they actually are because relativity is stretching out their journey. It's like watching a cosmic speed illusion where the rules of time and space get twisted. But blazars aren't just flashy light shows, they're time capsules. The light from Markarian 501 took 730 million years to reach us, meaning we're seeing it as it was before multicellular life existed on Earth. And yet, despite that vast distance, its jets still carry enough energy to affect our atmosphere when they flare up. These aren't just distant oddities, they're proof that the universe's fastest objects aren't just breaking speed records, they're rewriting the story of how energy moves across the cosmos. Black holes aren't just cosmic vacuum cleaners lurking in the centers of galaxies. Sometimes they become the universe's ultimate runaway freight trains. Picture this, a supermassive black hole weighing as much as 1 billion suns gets hurled through space at 5,000 kilometers per second. That's fast enough to travel from New York to Los Angeles in under a second. These aren't theoretical scenarios, astronomers have caught them in the act, leaving behind trails of chaos and creation. Take the case of the Runaway black hole spotted by Hubble in 2022. This monster wasn't just moving, it was fleeing the scene of a galactic collision, tearing through space so violently it left a 200,000 light-year long scar of newborn stars in its wake. That's longer than the entire Milky Way's diameter. Here's how it happened. When two galaxies merged, their central black holes spiraled toward each other, locked in a gravitational dance. But instead of merging, a third galaxy's black hole crashed the party, slingshotting one of them away at unimaginable speeds. The ejected black hole didn't leave quietly. It's gravity-compressed gas along its path like a cosmic snowplow, triggering star formation in a dazzling straight line. What's mind-blowing isn't just the speed, it's the sheer scale of destruction and creation. The black hole's trail isn't just a wound, it's a stellar nursery with clusters of young stars glowing blue against the void. Normally, star formation is a messy, chaotic process, but here it's been funneled into a perfect corridor, like a high-speed artist dragging a brush across the canvas of space. And because black holes themselves are invisible, we only see the aftermath, the glowing evidence of their passage written in starlight. This phenomenon challenges everything we thought we knew about galactic evolution. Runaway black holes aren't just rare accidents, they're proof that galaxies grow through violence, their histories written in high-speed ejections and collisions. That 200,000 light-year trail, it's more than a cosmic oddity, it's a fossil record of a moment when gravity itself went rogue, flinging a monster across the cosmos and painting the universe with new stars in its wake. Deep in the void of space, invisible bullets are constantly raining down on Earth cosmic rays, subatomic particles screaming through the cosmos at velocities so extreme they make pulsars look sluggish. These aren't just fast, they're the universe's ultimate speed demons, some traveling at 99.9% the speed of light. And here's the kicker, most of them are just single protons, tiny specks of matter packing energy that defies belief. Take the infamous "Oh my God" particle detected over Utah in 1991. This single proton hit Earth's atmosphere with the kinetic energy of a baseball hurled at 100 kilometers per hour. Let that sink in. A particle a quadrillion times smaller than a grain of sand delivered the punch of a fastball. How? Because at these ludicrous speeds, relativity takes over. As objects approach light speed, their energy doesn't just increase, it skyrockets exponentially. That proton wasn't just moving fast, it was a microscopic freight train with enough energy to briefly outshine a small star upon impact. But where do these particles get such insane velocities? The leading theory points to shockwaves from supernova explosions, cosmic particle accelerators far more powerful than anything we've built on Earth. When a star goes supernova, it creates expanding shock fronts that can slingshot protons to near-light speeds over thousands of years. Other candidates include active galactic nuclei, where black holes fling particles into space with forces we can barely comprehend. And sometimes these particles don't just travel, they ricochet off magnetic fields in space, gaining speed with each cosmic pinball bounce until they're moving at velocities that bend the laws of physics. What's truly wild is how common this extreme speed is. Earth's atmosphere is constantly bombarded by high-energy cosmic rays, about 1 per square meter every second. Most are lower energy, but the occasional "oh my God" outlier reminds us just how violent the universe can be. These particles don't just pass through us unnoticed, they create cascades of secondary particles when they hit the atmosphere, sparking air showers that span kilometers. Scientists detect them using arrays of sensors that pick up the faint glow of these high-speed collisions, turning the entire sky into a laboratory for studying nature's ultimate speed limit. But here's the cosmic mystery. Some of these particles exceed what we thought was possible. The "oh my God" particle's energy was so high, it shouldn't exist under current astrophysical models. At those energies, protons should interact with cosmic microwave background radiation and lose momentum long before reaching Earth, yet here they are, defying expectations. This means one of two things. Either our understanding of particle physics is incomplete, or there are cosmic accelerators out there far more powerful than supernovas, lurking in the darkness and flinging matter at speeds we can't yet explain. So while light may hold the universal speed record, these cosmic rays are the universe's way of showing us that even the smallest things can break the rules or reveal new ones. Every high-energy particle hitting our atmosphere is a message from deep space, written in velocities we're only beginning to decode. And somewhere out there, an even faster particle might already be racing toward us, ready to rewrite the textbooks once again. Even quasars, those brilliant beacons powered by ravenous supermassive black holes, have a dark side. Their winds, not gentle breezes, but supersonic tempests racing outward at 20% the speed of light, hot enough to vaporize entire solar systems and powerful enough to reshape galaxies. These aren't just fast, they're cosmic sandblasters, stripping galaxies of the raw materials needed to birth new stars and leaving behind galactic deserts in their wake. Take the quasar SDSS J1106 plus 1938, whose winds were clocked at a staggering 26,000 kilometers per second. At that speed, gas clouds torn from the quasar's accretion disk could cross the distance from Earth to the Sun in under 6 hours. But here's what's truly unsettling: these winds don't just dissipate. They crash into surrounding interstellar gas like a tsunami, compressing some regions while evacuating others, triggering chaotic shock waves that ripple across thousands of light years. The force is so immense, it can halt star formation not just locally but across entire galactic neighborhoods. This process, called quasar feedback, is one of the universe's most dramatic examples of self-regulation. A quasar's black hole feasts on surrounding matter, but in doing so, it fires back jets and winds so energetic they eventually starve the black hole itself. It's like a fire so intense it blows away its own fuel. Over eons, this cycle prevents galaxies from growing too large, solving a mystery that long puzzled astronomers: why there aren't more colossal galaxies in the universe. The answer: quasar winds act as cosmic governors, putting a speed limit on galactic growth. What's eerie is how permanent these changes can be. In the galaxy Markarian 231, quasar winds have cleared a cavity spanning 40,000 light-years, a void where star formation has effectively ceased. Gas that could have formed billions of stars now drifts uselessly into intergalactic space, all because of winds that began blowing when Earth's continents were still forming. Yet this destruction isn't meaningless. By suppressing star birth, quasar winds ensure remaining gas collapses more efficiently, leading to fewer but brighter stars, sculpting galaxies into the diverse shapes we see today. The legacy of these winds isn't just in what they destroy, but what they create. As they ram through galaxies, they forge heavy elements and fling them far beyond their host galaxies, seeding the cosmos with the building blocks for future planets and life. So while quasar winds might seem like agents of chaos, they're also the universe's way of recycling, ensuring that even the fastest, most destructive forces have a role in the story of creation. Among all the universe's speed demons, neutrinos might be the stealthiest, ghostly particles so light and fast they barely notice the cosmos exists. Born in the hearts of exploding stars, these subatomic phantoms can race through entire planets like they're not even there, hitting nearly the speed of light with barely a whisper. But in 1987, Earth got front-row seats to their greatest performance. A neutrino burst from supernova 1987 that arrived hours before the explosion's visible light, rewriting how we understand stellar death. Here's what made that moment so revolutionary. When a massive star collapses into a supernova, its core doesn't just explode, it first implodes, squeezing protons and electrons into neutrons and neutrinos with such force that trillions of these particles erupt outward. Unlike light, which gets bogged down battling through the star's outer layers, neutrinos zip straight through like cosmic lasers, barely slowed by anything. That's why detectors on Earth picked up 19 neutrinos from 1987, a full 3 hours before telescopes caught the first flicker of visible light. Those particles didn't just win the race, they were basically cheating physics by ignoring obstacles altogether. The detectors that spotted them weren't designed for supernovas at all. Buried deep underground to shield from interference, they were built to study proton decay until 1987, when neutrino counts suddenly spiked across Japan, the US, and Russia simultaneously. In less than 13 seconds, 24 neutrinos streaked through Earth, their energies matching exactly what models predicted for a collapsing stellar core. That precision was the smoking gun. For the first time, humanity had witnessed a star's death through two different cosmic messengers, with the invisible signal arriving first. What's wild is how much these ghostly particles revealed. By timing the delay between neutrinos and light, physicists confirmed how supernova unfold core collapse happens first, followed by a shockwave that takes hours to reach the surface and become visible. Neutrinos don't just travel fast, they're cosmic informants carrying secrets about processes hidden deep inside stars. And their speed isn't just impressive, it's nearly untouchable. In 1987, neutrinos were moving at 99.9999999% of light speed, missing the ultimate limit by less than 1/1000%. But here's the twist: despite their speed, neutrinos aren't perfect messengers. They oscillate between three flavors mid-flight, changing identities like undercover agents. That means the handful detected in 1987 were just a fraction of the total burst. Most had morphed into forms our detectors couldn't see. Yet even that flaw turned into a breakthrough, proving neutrinos have mass, however infinitesimal. So while they'll never dethrone light as the universe's speed champion, neutrinos hold their own title, nature's most elusive high-speed couriers, carrying whispers of stellar collapse across the cosmos faster than anything made of matter ever could. If you think pulsars and quasars are fast, gamma-ray bursts make them look like snails. These are the universe's ultimate explosive events, cosmic detonations so powerful they outshine entire galaxies for a few fleeting seconds, packing more energy than our sun will emit in its entire 10-billion-year lifetime. But what makes them truly staggering isn't just their brightness, it's the blistering jets they fire into space at 99.999% the speed of light. That's not just fast, it's the final decimal point before physics itself breaks. Take GRB 080319b, a gamma-ray burst recorded in 2008. In just 30 seconds, it released enough energy to outshine 1,000,000 trillion suns, all channeled into twin beams narrower than a laser pointer. Those jets weren't just bright. They were relativistic blowtorches, so focused that if one happened to hit Earth from thousands of light years away, it would strip our ozone layer in seconds. The force behind them comes from collapsing massive stars or merging neutron stars, where unimaginable gravitational forces twist magnetic fields into cosmic particle accelerators far more powerful than anything we could build. What's wild is how these jets form. As a dying star collapses into a black hole, its rotation flattens surrounding matter into a disk spinning nearly at light speed. The energy has to go somewhere, so it erupts outward along the star's poles, funneled by magnetic fields into beams so narrow they'd appear pencil-thin even from light years away. And because they're moving so close to light speed, relativity warps our view of them. Time in the jet's frame slows to a crawl, making the burst appear longer to us than it really is, like watching a high-speed replay in slow motion. But gamma-ray bursts aren't just cosmic curiosities, they're extinction-level threats. Evidence suggests one may have hit Earth 450 million years ago, triggering mass extinctions by irradiating the planet's surface. The good news: they're incredibly rare in our galaxy. The bad news: we've detected them from billions of light years away, meaning their power is almost beyond comprehension. And here's the kicker: we're seeing them long after they've happened. By the time their light reaches us, the actual explosion is ancient history, leaving behind only a fading afterglow and a reshaped corner of the cosmos. Yet these bursts also play a cosmic role. The heavy elements forged in their violence, gold, platinum, uranium, are flung across space, eventually seeding new stars and planets. Without gamma-ray bursts, the universe might lack the ingredients for rocky worlds like ours. So while they're terrifying in scale, they're also proof that even the fastest, most destructive events in existence can be creators in disguise, sculpting the universe at speeds where time itself starts to bend. Fast radio bursts are the universe's most mysterious speed demons, blasts of radio waves so intense they outshine entire galaxies in milliseconds, then vanish without a trace. For years, these fleeting signals puzzled astronomers, appearing randomly from deep space with no clear source. Then in 2020, everything changed when a magnetar in our own Milky Way, a highly magnetized neutron star, sent out a burst that matched the profile of a fast radio burst, solving part of the mystery while opening new questions about just how much energy these cosmic flashes can unleash. Take FRB 200428, the first fast radio burst ever traced to a known object. This millisecond pulse came from magnetar SGR 1935 + 2154, 30,000 light-years away in the constellation Vulpecula. In less time than it takes to blink, it released as much energy as the sun does in 30 seconds, except this wasn't sunlight, but focused radio waves packing the punch of a gamma-ray burst. The magnetar didn't just flicker, it cracked like a cosmic whip, its magnetic field snapping with such violence that it shook space-time itself, sending ripples through the fabric of reality that we detected as a blip on our radio telescopes. What makes magnetars perfect suspects for these bursts is their unimaginable magnetic fields. A typical neutron star already has a magnetic field 1 trillion times stronger than Earth's, but a magnetar cranks that up another 1,000 times. Picture the force needed to lift a freight train, now compress that into a space smaller than a sugar cube. At these extremes, the magnetic fields become so twisted they occasionally rupture the star's crust, triggering starquakes that release pent-up energy in sudden, violent bursts. FRB 200428 wasn't just a radio signal, it was the scream of a stellar corpse undergoing magnetic torture, a distress call written in frequencies we could finally decode. Yet fast radio bursts from distant galaxies are another beast entirely. While our Milky Way's magnetar confirmed one potential source, the brightest extragalactic bursts dwarf even FRB 200428 by factors of billions. Some last just microseconds but pack enough energy to power human civilization for centuries. The leading theory, some might involve magnetars plunging into black holes or colliding neutron stars, events so catastrophic they warp magnetic fields into cosmic particle accelerators, funneling energy into tight radio beams that cross the universe like laser pointers aimed at Earth. The real enigma is why some bursts repeat while others never reappear. FRB 121102, discovered in 2012, fires off bursts like clockwork every 157 days, a cadence suggesting orbital motion, perhaps around another star or black hole. Others, like the infamous Lorimer burst, have never been heard from again, leaving astronomers wondering if they witnessed the death throes of some unknown celestial object. This duality hints that fast radio bursts might be multiple phenomena wearing the same disguise, some born from magnetar tantrums and others from rarer, more apocalyptic events. What's certain is that these bursts aren't just cosmic fireworks, they're tools. As they race through intergalactic space, their waves interact with sparse electrons, slowing slightly in ways that reveal the universe's hidden matter. By measuring these delays, astronomers have mapped the cosmic web, the vast filaments of gas connecting galaxies. The fact that we can detect bursts from billions of light-years away means they're piercing through regions of space we've never probed, turning each millisecond flash into a message bottled in the purest form of speed the universe can muster. So while magnetars like SGR 1935 + 2154 gave us the first clues, fast radio bursts remain one of space's greatest puzzles, proof that even the fastest, briefest signals can carry the weight of cosmic secrets. Every new detection peels back another layer, revealing a universe more violent, more magnetic, and more astonishingly precise than we ever imagined. Gravity isn't just a force, it's a cosmic messenger, rippling through space-time itself at the speed of light. In 2015, humanity gained a new sense when LIGO, the Laser Interferometer Gravitational Wave Observatory, detected the faintest whisper of these ripples, a signal from two black holes colliding 1.3 billion years ago. The event lasted just 0.2 of a second, but it rewrote astronomy forever. This wasn't light, sound, or any particle we know. It was space itself stretching and squeezing like a drumhead, carrying the echoes of a violent merger across the cosmos. Picture the scale of what LIGO heard. Those black holes, each about 30 times the sun's mass, spiraled toward each other at half the speed of light before merging in a cataclysm so powerful it briefly outshone every star in the observable universe combined. The energy released warped the fabric of space-time, sending vibrations outward at light speed, not through space, but as distortions of space itself. By the time they reached Earth, the waves had weakened to near nothingness, stretching LIGO 4-kilometer arms by less than 1,000th the width of a proton. That's like measuring the distance to Alpha Centauri down to the width of a human hair. What makes gravitational waves so revolutionary is how they travel. Unlike light, which gets absorbed or scattered by dust and gas, these waves pass through everything unimpeded. A black hole merger behind a galaxy, gravitational waves don't care. The heart of a nebula too dense for telescopes to pierce, the waves slice right through. They're the universe's ultimate couriers, delivering secrets from places electromagnetic waves can't reach. And because they move at light speed, they're perfectly synchronized with the events they describe. No cosmic delays, no distortion. Since that first detection, LIGO and its European counterpart Virgo have caught dozens more mergers, including the smash-up of 2 neutron stars in 2017. That event was a Rosetta Stone for astronomy. Gravitational waves arrived first, followed 2 seconds later by a gamma-ray burst, then a glow across every wavelength from radio to X-rays. For the first time, we saw the same cosmic cataclysm through multiple senses, proving that heavy elements like gold and platinum are forged in these collisions. The gold in your jewelry, it might have been born in a neutron-star merger, flung into space by gravitational waves racing ahead like cosmic heralds. But here's the mind-bending part. Gravitational waves don't just reveal hidden events, they let us hear the universe's shape. The pitch and rhythm of a wave's chirp tell us the masses of the colliding objects, their spins, even how far away they are. It's like celestial sonar, painting pictures with vibrations instead of light. Future detectors like space-based LISA will tune into lower frequencies, catching the mergers of supermassive black holes and possibly echoes from the Big Bang itself. We're not just observing the cosmos anymore, we're feeling its vibrations, listening to the subtle hum of space-time bending under the weight of its most violent dances. So while light may still be the universe's fastest traveler, gravitational waves are its most untouchable ripples that move through walls, carry unfiltered truth, and remind us that even empty space isn't truly still. Every detection is a postcard from the edge of physics, written in distortions we're only beginning to decode. The sun might seem steady from our vantage point, but it's constantly hurling its own high-speed projectiles across the solar system. During massive solar storms, our star accelerates protons to 80% the speed of light, creating invisible cosmic bullets that pose serious risks to anything in their path. Unlike the gentle warmth we feel on Earth, these particles pack enough punch to fry satellite electronics, threaten astronauts with dangerous radiation doses, and even trigger breathtaking auroras that dance at the poles. Take the Carrington event of 1859, the most powerful solar storm ever recorded. The explosion was so intense, it hurled particles toward Earth at speeds approaching light, causing telegraph systems worldwide to spark and fail. Imagine that happening today to our power grids and communication networks. Modern satellites caught similar but smaller events, like the 2012 solar flare that barely missed Earth. Data showed its protons reached 80% light speed within minutes, a velocity so extreme it would take just 15 seconds for them to travel from the Sun to Earth. At those speeds, a single proton carries the kinetic energy of a Major League fastball, crammed into a particle a quadrillion times smaller. For astronauts outside Earth's protective magnetic field, these storms are deadly serious. The International Space Station often takes shelter in more shielded sections during solar events, but a moon base or Mars mission wouldn't have that luxury. Unprotected, an astronaut could absorb a year's worth of radiation in just hours, increasing cancer risks and potentially causing acute radiation sickness. Even spacecraft aren't safe. Solar protons can penetrate hulls, scrambling computer memory and degrading solar panels over time. That's why missions like the Parker Solar Probe are crucial. By studying the Sun up close, we're learning how to predict these particle barrages before they strike. Yet there's beauty in this chaos. When these high-speed protons collide with Earth's atmosphere near the poles, they ignite the shimmering curtains of light we call auroras. The vivid greens and reds come from oxygen and nitrogen atoms absorbing that energy and re-emitting it as light, nature's way of turning a violent solar storm into a celestial light show. During intense events, auroras can stretch far beyond their usual polar homes, dazzling observers as far south as Cuba or Spain. But here's the twist: not all solar particles move at the same speed. Electrons, being lighter, often outpace protons, arriving at Earth minutes earlier like cosmic warning shots. Scientists use this delay to forecast when the heavier, more dangerous protons will hit, buying precious time to protect vulnerable systems. It's a high-stakes race against the universe's fastest particles, one where understanding speed isn't just about physics but survival. So while solar flares might seem distant, their high-speed protons are a reminder that our star is anything but serene. From threatening technology to painting the skies with otherworldly colors, these particles connect us to the Sun's fury in ways we're still learning to navigate, proving that even at 80% light speed, the universe never fails to surprise us. Imagine standing on a distant world where the wind doesn't just howl, it screams past you at over 8,700 kilometers per hour, carrying not rain but shards of molten glass. This isn't science fiction, it's the brutal reality of HD 189733b, an exoplanet where the weather would make Jupiter's great red spot look like a gentle breeze. Located 63 light-years away, this cobalt-blue gas giant orbits so close to its star that its atmosphere is literally boiling away, creating winds that move at 2 kilometers per second, 7 times the speed of sound. Put that into perspective, the fastest winds ever recorded on Earth during the 1999 Bridge Creek Moore tornado maxed out at about 500 kilometers per hour. That's devastating enough to rip homes from their foundations, but HD 189733b's winds are 17 times stronger. They don't just push, they obliterate. And what's blowing in those winds? Silicate particles, superheated to over 1,000 degrees Celsius, condensing into tiny glass droplets midair. The result? Horizontal storms where it rains molten glass, not in gentle droplets, but in hypersonic, sideways-fired needles that would instantly shred any spacecraft daring to enter. What fuels these insane winds? The planet's extreme temperature contrasts. One side, permanently locked toward its star, bakes at 930 degrees Celsius, while the night side simmers slightly cooler. This temperature differential creates a pressure gradient so steep it whips the atmosphere into a frenzy, like a cosmic steam engine with no off switch. Unlike Earth, where jet streams meander, HD 189733b's winds form a single planet-spanning supercurrent, racing unhindered from day to night and back again. The real shocker: astronomers detected these winds not by seeing them but by listening. Using the Doppler effect, the same principle that makes a siren's pitch change as it passes, they measured minute shifts in the light filtering through the planet's atmosphere. The data revealed atoms being dragged at unimaginable speeds, painting a portrait of a world where the sky itself is a weaponized blizzard of glass. Yet this exoplanet isn't just a cosmic curiosity, it's a warning. HD 189733b shows what happens when a planet orbits too close to its star, a fate that might await worlds in tighter systems. As we search for Earth-like exoplanets, this cobalt hellscape reminds us that not all blue planets are havens. Some are hurricanes of death wrapped in a deceptively serene hue, proving once again that the universe's fastest things aren't just in deep space. Sometimes they're hidden in plain sight, masquerading as jewels in the cosmic dark. Here we are, sitting on what feels like a perfectly still planet, yet we're actually riding a cosmic carousel moving at 828,000 kilometers per hour. That's the speed at which our solar system whips around the center of the Milky Way, caught in the galaxy's grand rotation. To put that ludicrous velocity into perspective, you're currently moving about 230 times faster than a bullet fired from a rifle just by existing on Earth. And here's the real kicker, this isn't some gentle cruise. The Milky Way's spin is so powerful, it flings entire star systems through space in a carefully orchestrated gravitational dance, one that takes a staggering 230 million years to complete just one full orbit. Think about what that means for cosmic timekeeping. The last time our solar system was in this exact position within the galaxy, dinosaurs were the dominant land animals. The continents were still huddled together in the supercontinent Pangaea. Flowering plants hadn't even evolved yet. When we complete our next full galactic orbit, who knows what life, if any, will be around to witness it. This timescale dwarfs human history so completely, it forces us to confront just how fleeting our existence is in the grand scheme of the cosmos. The mechanics behind this motion are just as fascinating as the numbers. The Milky Way doesn't spin like a rigid disk, it's more like a celestial whirlpool, with stars closer to the center completing orbits faster than those farther out. Our position about 27,000 light-years from the galactic core puts us in what astronomers call the corotation radius, where the speed of the spiral arms and the stars roughly matches up. If we were much closer, we'd be whipping around so fast that gravitational chaos might disrupt planetary orbits farther out, and we'd risk being left behind in a lonelier, star-poor region of the galaxy. Instead, we're in a galactic sweet spot, riding a wave of stability in an otherwise dynamic and ever-changing stellar environment. But here's what's truly mind-bending. Despite these insane speeds, we don't feel a thing. There's no cosmic wind rushing past our faces, no sense of motion at all. That's because everything in our neighborhood, the sun, nearby stars, even the sparse gas between them, is moving together, locked in the same gravitational flow. It's like being on a smoothly moving train where the scenery outside might blur, but inside, your coffee stays perfectly still in its cup. This shared motion is why ancient astronomers never noticed our galaxy's spin. Without fixed reference points beyond the Milky Way, the rotation was invisible until modern telescopes revealed the subtle Doppler shifts of distant stars. And don't assume our path is a perfect circle. The Milky Way's spiral arms, giant molecular clouds, and even dark matter lumps tug on us as we move, creating slight wobbles in our orbit. Over millions of years, these perturbations might subtly alter Earth's cosmic environment, potentially influencing everything from comet showers to the intensity of cosmic rays reaching our planet. Some theories even suggest these periodic galactic bumps could correlate with mass extinctions, though that's still hotly debated. So the next time you gaze up at the night sky, remember, you're not just looking at the stars, you're racing past them at nearly 1,000,000 kilometers an hour, carried along by a galaxy whose full rotation spans eras longer than most life forms have existed on Earth. It's a humbling reminder that even when we feel stationary, the universe is always in motion, and we're along for the ride. While we're hurtling around the Milky Way at breakneck speeds, there's an even more dramatic cosmic collision course unfolding right next door. The Andromeda Galaxy, our closest galactic neighbor, is barreling toward us at 110 kilometers every second, fast enough to cross the entire United States in under a minute. At that rate, you'd expect an imminent crash, but here's the twist. Space is so unimaginably vast that this high-speed approach will take 4 billion years to culminate in a full galactic merger. This isn't just two galaxies drifting together. It's a carefully choreographed dance governed by gravity's invisible pull. Current measurements from the Hubble Space Telescope show Andromeda's outer halo already brushing against the Milky Ways, like two swimmers slowly closing the distance in a dark pool. When the main event happens, the actual stars won't collide because of the enormous distances between them. Instead, their mutual gravity will twist and warp both galaxies into spectacular new shapes, flinging stars into long tidal tails that glitter across the cosmos. Computer simulations reveal what this slow-motion smash-up might look like. Initially, the galaxies will pass through each other like ghosts, their gravity distorting their spiral arms into chaotic ribbons. Then, over hundreds of millions of years, they'll swing back for a series of closer passes, each orbit tightening until the two cores finally merge into a single, enormous elliptical galaxy some astronomers have nicknamed Milkdromeda. Our Sun will likely get flung much farther from the galactic center than it is today, giving any future Earthlings a front-row seat to a sky filled not with a neat band of stars, but with a dazzling, irregular swarm. What's truly wild is how this collision will reshape our cosmic neighborhood. The merger will trigger a frenzy of new star formation as gas clouds compress, potentially birthing millions of new stars, though by that time, our Sun may have already expanded into a red giant, rendering Earth uninhabitable. Dark matter halos around both galaxies will merge too, creating an invisible scaffold that determines the new galaxy's final shape. Andromeda's central black hole, currently about 100 million solar masses, will eventually spiral toward the Milky Way's 4 million solar mass black hole, creating gravitational waves that ripple across the universe. Yet even as these giants merge, the universe keeps expanding. Other galaxies beyond our local group are speeding away so fast that they'll never witness this spectacle. In the grand scheme of things, the Andromeda-Milky Way collision is just a small-scale event, two neighbors in an emptying cosmic village drawing closer for warmth. But for us, it's a reminder that even the fastest motions in space often play out on timescales beyond human comprehension, where imminent means waiting longer than life has existed on Earth. While stars and galaxies dazzle us with their visible light, the real cosmic heavyweight champion moves in complete darkness, swirling through space at 220 kilometers per second, yet leaving no trace except its gravitational pull. These aren't rogue planets or stealthy black holes, they're dark matter particles, the universe's invisible architects, whirling through vast halos surrounding every galaxy. Their breakneck speeds aren't random, they're precise cosmic clues allowing scientists to map the hidden scaffolding holding the universe together. Imagine trying to study something that doesn't emit, reflect, or absorb light, a substance that makes up 85% of all matter in the cosmos yet remains utterly invisible to our telescopes. The trick lies in watching how dark matter's gravity influences the things we can see. Stars on the outer edges of galaxies, like our Milky Way, rotate far faster than they should based on visible matter alone. The only explanation, an immense halo of dark matter envelops each galaxy, its gravitational grip keeping stars from flying off into intergalactic space. The speed of these stars, some clocking over 200 kilometers per second, betrays the presence of something far more massive than meets the eye. Here's where it gets brilliant. By measuring how fast stars and gas clouds orbit galactic centers, astronomers can essentially weigh the dark matter halo's influence. The velocities follow a predictable pattern, Stars closer to the center move slower, while those farther out speed up, plateauing around that magic 220 km/s mark. This rotation curve is the smoking gun, proof that an invisible mass stretches far beyond a galaxy's luminous disk. Without dark matter's gravitational anchor, galaxies would have torn themselves apart billions of years ago, their outer stars flung away by centripetal force. The Bullet Cluster offers perhaps the most striking evidence. When two galaxy clusters collided, their visible gas clouds slammed together and slowed down, but the dark matter detected through gravitational lensing kept racing ahead at those same blistering speeds. This cosmic hit and run left dark matter separated from normal matter like footprints in the snow, proving it interacts only through gravity. Those high speeds weren't incidental. They revealed dark matter's true nature, a substance that outruns even the violence of galactic collisions. But dark matter's velocity isn't just about gravity. It's a time capsule from the early universe. Simulations show these particles must have been moving sluggishly in the cosmic dawn, allowing them to clump together and form the seeds of galaxies. If they'd moved too fast early on, they would have escaped their own gravitational pull, preventing structure from forming. That delicate balance, fast enough to shape galaxies today, but slow enough to build them in the past, is why scientists think dark matter might be cold, with particles moving just below relativistic speeds. Mapping these invisible halos has revolutionized cosmology. When astronomers compare the speeds of distant galaxies to the cosmic microwave background, they can trace how dark matter's gravitational web has stretched and evolved over billions of years. It's like watching shadows move across a cave wall to deduce the shapes outside, except here, the shadows are whirlpools of stars, and the unseen sculptor is a substance whose nature still eludes us. Every high-speed particle in those halos is a messenger from the dark side of the universe, whispering secrets about the architecture of existence itself. So while we may never see dark matter directly, its fingerprints are everywhere in the spin of galaxies, the bend of starlight, and the grand tapestry of cosmic structure. Those 220 km/s halos aren't just curiosities. They're the hidden choreographers of the cosmos, dictating the motions of everything bright enough for us to see. And as we peel back their mysteries, we're not just studying dark matter, we're reading the instruction manual for how the universe builds itself. Kepler 70b isn't just fast, it's a cosmic daredevil, skimming so close to its star that a full year there lasts less than 6 hours. This scorched world rockets through space at 800,000 km/h, completing an entire orbit in the time it takes you to watch a long movie. To put that absurd speed into perspective, if Earth moved this fast, we'd zip around the Sun in just over 3 days instead of 365. But Kepler 70b's velocity comes at a brutal cost. Its surface is a broiling wasteland, heated to over 7,000 degrees Celsius, hotter than some stars and enough to vaporize iron instantly. What keeps this exoplanet tethered to its star at such breakneck speeds? Extreme gravitational forces. Kepler 70b orbits the remnant core of a red giant star, now shrunk into a hot subdwarf no larger than Earth but packing half the Sun's mass. This dense stellar corpse grips the planet with unrelenting gravity, whipping it around like a tetherball on a cosmic playground. So close is Kepler 70b that its star looms 70 times larger in its sky than our Sun appears from Earth, a searing, white-hot monstrosity filling half the heavens. The planet's fate is even stranger than its speed. Tidal forces have locked one side permanently toward the star, creating a day side where temperatures reach double those on the Sun's surface, and a night side that's marginally cooler but still hotter than lava. There's no atmosphere to redistribute the heat. It's been long since blasted away by stellar radiation, leaving behind what scientists suspect might be a naked core of molten heavy metals, a planetary skeleton stripped to its bones. Yet Kepler 70b wasn't always this inferno. Astronomers believe it was once a gas giant like Jupiter, orbiting farther out until its dying star expanded during its red giant phase, swallowing inner planets and dragging Kepler 70b inward. When the star shed its outer layers, the planet survived, left stranded in this hellish close orbit. Now it's slowly evaporating, its remaining material trailing behind it like a comet's tail, a cosmic speedster on borrowed time. What's fascinating isn't just its velocity, but what it reveals about planetary survival. Kepler 70b defies expectations by existing at all. Conventional models say planets shouldn't endure such violent stellar evolution. Its very presence forces astronomers to rethink how planetary systems behave when their stars near death. Every scorching orbit is a high-speed laboratory, testing the limits of what can withstand the universe's extremes. So while Kepler 70b might seem like a cautionary tale of celestial excess, it's also a testament to resilience. Even as it spirals toward eventual destruction, this blazing speed demon teaches us that planets can endure and even thrive in conditions we once thought impossible. Its breakneck dance with death reminds us that the universe's fastest objects aren't just about velocity, they're about rewriting the rules of existence itself. Some galaxies aren't just making stars, they're vomiting them into space at speeds that defy imagination. Take starburst galaxy M82, a cosmic fireworks factory where stars are born 10 times faster than in our Milky Way. But this frenzy of creation comes with violent consequences. The sheer energy from supernova explosions and young, massive stars has blasted a hurricane of gas outward at 1,000 kilometers per second, fast enough to cross the continental United States in under 4 seconds. These aren't gentle breezes, they're galactic superwinds, tsunamis of raw star stuff screaming into intergalactic space, carrying enough material to build millions of new solar systems. What makes M82's winds so extreme? Look toward its core, where stars are packed so tightly they're practically shoulder to shoulder. When these stars die, some after just a few million years, their supernova shockwaves don't dissipate quietly. Instead, they combine like overlapping explosions in a chain reaction, creating a pressure cooker that launches gas outward in opposite directions. Hubble Space Telescope images reveal this chaos in stunning detail. Filaments of ionized hydrogen stretching 40,000 light-years into space, glowing red-hot as they're shredded by turbulence. It's like the galaxy has two giant exhaust pipes spewing its own insides into the void. But here's the twist, these winds aren't just destruction, they're part of the universe's grand recycling program. The gas they carry, enriched with heavy elements forged in stellar cores, eventually slows down and mixes with the cooler hydrogen floating between galaxies. Over billions of years, gravity pulls these metal-rich clouds back into galactic halos, where they collapse to form new stars with planets and potentially life. The iron in your blood, the calcium in your bones, those atoms might have once ridden a superwind out of a galaxy like M82 before looping back into a newborn solar system. The scale of this process beggars belief. A single starburst galaxy can eject the mass of 10 million suns in just 10 million years. That's enough material to seed entire galactic neighborhoods with the building blocks for future stars. Astronomers have even spotted these outflows in the early universe, where young galaxies relied on superwinds to self-regulate, blowing away gas to prevent runaway star formation that would otherwise burn through their fuel too quickly. It's a cosmic balancing act. Too much wind and a galaxy starves itself, too little, and it chokes on its own stardust. What's fascinating is how these winds shape their surroundings. As M82's superwind plows into surrounding gas, it creates shock fronts that glow in X-rays visible to telescopes like Chandra. These collisions forge molecules you'd never expect in the harsh environment of intergalactic space, including water and complex organic compounds. Far from sterile voids, the regions around starburst galaxies might be chemical factories, brewing ingredients for life where no stars currently shine. So while galactic superwinds might seem like apocalyptic events, they're actually vital threads in the cosmic web. Without them, galaxies would burn out too fast, and the universe would lack the diversity of elements needed for planets and people. M82's 1,000 km/s tantrum isn't just chaos. It's the universe's way of turning destruction into creation, proving once again that even the fastest, most violent phenomena have a purpose in the grand scheme. Most stars die quietly, fading into darkness, but LP 4365 is different. This cosmic survivor didn't just endure a supernova, it got hurled across space at 5 million km/h, leaving its explosive past in the dust. Astronomers call it a zombie star, a white dwarf that somehow cheated death after a cataclysm powerful enough to obliterate most stellar remnants. Now, it's racing through the Milky Way like a bullet, its trajectory betraying the violence of its origin. Picture the moment of its escape. When a white dwarf steals too much mass from a companion star, it can trigger a runaway thermonuclear explosion, a Type Ia supernova. Normally, these blasts leave nothing behind, but LP 4365 is evidence of an incomplete detonation, a supernova that somehow failed to fully destroy its progenitor. Instead of vanishing, the star got punted across the galaxy, its outer layers scorched off but its dense core intact. The kick was so powerful it reached 1% of light speed, enough to cover the distance from Earth to Pluto in less than a day. What's left is bizarre even by cosmic standards. Spectral analysis reveals a surface unlike any normal white dwarf, a patchwork of heavy elements like neon, oxygen, and magnesium forged in the explosion. It's as if the star's guts were flash-cooked and then splattered across space, leaving a trail of atomic evidence in its wake. The sheer velocity suggests the supernova wasn't symmetrical. The explosion must have been lopsided, like a cosmic cannon recoiling as it fired the star into the void. This zombie star isn't just a curiosity, it's a clue. By studying its composition, astronomers can piece together how some white dwarfs survive explosions meant to annihilate them. Its trajectory, angled steeply out of the Milky Way's disk, hints at a violent birth in a binary system that no longer exists. The companion star, either obliterated or flung in the opposite direction, a cosmic divorce finalized at 5 million km/h. What awaits LP 4365? Unlike most stars, it won't orbit the galaxy indefinitely. Its speed exceeds the Milky Way's escape velocity, meaning it's destined for intergalactic space. Over billions of years, it'll cool into a blackened cinder, drifting alone through the abyss between galaxies, a tombstone marking a supernova that wasn't quite fatal, and a star that refused to die quietly. Yet, even in its exile, this cosmic fugitive serves a purpose. Every element heavier than iron in its scarred surface tells a story of nuclear fires and impossible survival. For astronomers, it's a Rosetta Stone for understanding supernova mechanics, proof that sometimes when stars die, they leave behind more than just echoes. They leave survivors, and those survivors, like LP 4365, carry secrets about the universe's most violent moments written in their speed and scars. Oumuamua wasn't just passing through, it was blazing out of our solar system at 315,000 km/h, faster than any natural object we'd ever seen. This interstellar visitor, the first confirmed object from beyond our star system, didn't just defy expectations with its speed. It left astronomers scratching their heads over something even stranger, an unexpected acceleration as it departed. Most icy bodies would slow down as they moved away from the sun, but Oumuamua did the opposite. It sped up as if pushed by an invisible force, sparking debates that stretched from scientific journals to headlines wondering if we just witnessed our first brush with alien technology. The numbers alone were staggering. At its peak, Oumuamua was covering the distance from Earth to the Moon in less than 2 hours. By comparison, NASA's Parker Solar Probe, the fastest human-made object ever built, tops out at a mere 700,000 kilometers per hour, less than a quarter of Oumuamua velocity. But raw speed wasn't the real mystery. It was that inexplicable nudge as it left. Comets typically accelerate due to outgassing sunlight vaporizing their ice, creating jets that act like natural thrusters. Yet Oumuamua showed no visible coma or tail, no telltale signs of sublimating material. So what was propelling it? Some scientists proposed exotic natural explanations. Maybe Oumuamua was made of hydrogen ice, which could sublimate invisibly in sunlight, providing thrust without visible debris. Others suggested it might be a chunk of nitrogen ice sheared off a Pluto-like exoplanet, its surface boiling away in the sun's heat. But each theory had holes. Hydrogen ice should evaporate too quickly in interstellar space to survive its journey, while nitrogen-rich objects are statistically rare. The simplest explanation, that Oumuamua was a peculiarly shaped, inert rock, couldn't account for the acceleration at all. Then came the more provocative ideas. Harvard astrophysicist Avi Loeb famously suggested Oumuamua could be artificial, a light sail propelled by sunlight, perhaps debris from an advanced civilization. The shape seemed to fit. Telescopic data implied an elongated, possibly flat profile, ideal for catching solar radiation. But skeptics countered that extraordinary claims require extraordinary evidence, and Oumuamua's brief visit left too many gaps. Without a clear photo or spectroscopic signature, the truth remains tantalizingly out of reach. What's undeniable is how Oumuamua reshaped astronomy. Its speed and trajectory confirmed it came from another star system, making it the first known interstellar vagabond. Later discoveries, like the comet Borisov, proved such visitors aren't uncommon, but none have behaved like Oumuamua. Future telescopes like the Vera Rubin Observatory aim to catch these interlopers earlier, giving us time to study them before they vanish into the void. Oumuamua's legacy isn't just about one strange object. It's a reminder of how much we don't know, whether a cosmic iceberg, a shard of alien technology, or something even stranger. Its fleeting visit challenged our assumptions. As it races toward the constellation Pegasus at unfathomable speeds, it carries with it the ultimate lesson. The universe is full of surprises, and sometimes the fastest things aren't just breaking speed records, they're breaking our understanding of reality itself. Imagine a star moving so fast it could cross the entire United States in less than a second. That's S2, one of several stars caught in a death-defying dance around Sagittarius A, the supermassive black hole at the Milky Way's heart. Clocked at a staggering 18 million kilometers per hour, 2.5% the speed of light, this stellar daredevil doesn't just orbit. It slingshots around the black hole's event horizon in a gravitational roller coaster that bends both space and our understanding of physics. Tracking S2's breakneck motion has given astronomers a front-row seat to Einstein's theory of relativity in action. As the star reaches its closest approach, just 17 light hours from the black hole, relativity's effects become impossible to ignore. Time itself slows down for S2 as it screams through this extreme gravity well, an effect called gravitational time dilation. The star's light stretches to redder wavelengths, struggling to escape the black hole's pull like a runner fighting against a headwind. Even its orbit doesn't behave as Newton would predict. Instead of tracing a perfect ellipse, S2's path gradually spirals, tracing a rosette pattern that perfectly matches Einstein's equations. The most mind-blowing moment came in 2018 when S2's close pass made history. As it whipped around Sagittarius A, telescopes caught its light shifting to red then back to blue, a celestial speedometer proving the star accelerated to nearly 8,000 kilometers per second at closest approach. That's fast enough to travel from Earth to the Moon in under a minute, but the real triumph was how precisely this matched predictions. Over 16 years of observations, S2's orbit precessed by precisely the amount relativity demanded, delivering one of the most conclusive proofs that Einstein was right about how gravity warps space-time. These stars aren't just cosmic speedometers, they're black hole probes. By mapping their chaotic orbits, astronomers have weighed Sagittarius with incredible precision. 4.3 million solar masses packed into a space smaller than our solar system. Other S-stars orbiting even closer, like S62, complete their orbits in less than 10 years, offering even sharper tests of relativity. Some even dip so close that their outer layers get shredded by tidal forces, leaving glowing trails of stellar debris spiraling into the abyss. Yet the most tantalizing possibility remains just out of reach. If astronomers can track a star passing even closer, perhaps skimming just outside the event horizon, we might finally glimpse the mysterious gravitational redshift effect, where light becomes so stretched it fades from view entirely. That would be the ultimate validation of black hole physics, captured not in simulations but in the frantic dance of a star racing against the universe's most extreme forces. Every loop S2 completes isn't just an orbital period, it's another revolution in our understanding of gravity itself. When two neutron stars spiral together in a cosmic collision, they don't just merge, they detonate like atomic bombs forged in the heart of a star factory, flinging shrapnel into space at 30% the speed of light. But this isn't ordinary debris, it's gold, platinum, uranium, the heaviest elements in the universe, forged in the heart of the explosion and sprayed across the cosmos like treasures from a shattered vault. And in 2017, for the first time in history, humanity caught one of these kilonova explosions in the act, not just with telescopes, but by feeling the ripples in space-time itself. The event, catalogued as GW170817, started with a chirp, a rising crescendo of gravitational waves detected by LIGO and Virgo observatories as two neutron stars circled each other hundreds of times per second before merging. Less than 2 seconds later, NASA Fermi satellite spotted a gamma-ray burst from the same patch of sky. Telescopes worldwide swiveled to look, and what they saw rewrote astrophysics. The aftermath glowed like a celestial forge, its light curve shifting from blue to red over days as heavy elements decayed. A smoking gun proving that kilonovas are the universe's primary goldsmiths. Here's what makes these ejectors so extraordinary. The neutron-rich material flung outward doesn't just move fast, it's riding shockwaves so powerful they create nuclear reactions on the fly. Atoms capture neutrons in rapid succession, climbing the periodic table to form elements like gold and platinum before the expanding cloud even cools. Simulations suggest a single merger can produce hundreds of Earth masses worth of precious metals, some of it flung so far it eventually seeds entire galactic neighborhoods. That wedding ring on your finger, its atoms might have been born in a neutron star collision billions of years ago, ejected at a fraction of light speed before winding up in a cloud that formed our solar system. The 2017 event revealed something even wilder. These explosions aren't perfectly spherical. Hubble Space Telescope observations showed the ejector formed a lopsided plume, with some material moving toward us at relativistic speeds while other parts lagged behind. This asymmetry explains why the glow faded unevenly and hints that neutron star mergers might be even more efficient cosmic foundries than we thought. The fastest moving debris, rich in lighter elements like strontium and silver, raced ahead while gold and platinum trailed in denser clumps, painting the aftermath with distinct chemical signatures. But the real revelation was how kilonovas solve a cosmic mystery. Before GW170817, astronomers argued about where half the universe's heavy elements came from. Supernovas couldn't account for it all. Now we know neutron star mergers pick up the slack, scattering their metallic bounty so widely that even the earliest galaxies contain traces of gold. It's a process so violent, so precise, and so fast that it's almost poetic. A celestial alchemy where dying stars smash together to mint the universe's most coveted elements, then fling them into the void at speeds approaching the ultimate limit. So the next time you hold something made of gold, remember, you're touching stardust forged in one of the universe's most extreme events, hurled across space at unimaginable speeds and delivered to Earth by cosmic chance. Kilonovas don't just make gold, they're the universe's way of ensuring that even its most violent moments leave behind something beautiful. Most stars quake gently, if at all, but magnetas are the universe's ultimate seismic monsters. Picture a neutron star with a magnetic field so strong it could erase your credit card from halfway across the solar system. Now imagine that field twisting until it snaps, cracking the star's crust like a walnut shell and unleashing a gamma ray flare brighter than a million suns. That's a magneta starquake, a cosmic catastrophe where the energy release happens at light speed, bending the very rules of physics. The most notorious example hit Earth without warning on December 27, 2004. A magneta named SGR 1806-20, 50,000 light-years away in the constellation Sagittarius, unleashed a gamma ray burst so powerful it briefly outshone the full moon despite being halfway across the galaxy. In just 0.2 of a second, it released more energy than our Sun emits in 250,000 years. The pulse traveled at light speed for 50 millennia before slamming into Earth's upper atmosphere, ionizing gases 60 kilometers up and distorting radio transmissions worldwide. Satellites designed to detect nuclear tests went into alert mode, convinced someone had detonated a secret space weapon. What makes this event mind-blowing isn't just the distance, it's the physics behind the flare. Magnetas are neutron stars with magnetic fields 1,000 times stronger than ordinary pulsars, so intense they can literally rip spacetime apart. When their crusts fracture under magnetic stress, the resulting starquakes launch relativistic Alfvén waves ripples in the magnetic field that accelerate electrons to near light speed. These particles then spiral along magnetic field lines, emitting gamma rays in a process called synchrotron radiation. The entire chain reaction from crustal snap to gamma ray burst happens faster than a hummingbird's wing beat. The 2004 flare wasn't an isolated incident. Magneta bursts follow a pattern called the Christmas tree effect, where smaller precursor quakes build up to a catastrophic rupture, like tectonic plates grinding before a mega earthquake. But unlike terrestrial quakes measured on the Richter scale, magneta starquakes register on a logarithmic starquake scale, where each whole number represents a 10,000-fold energy increase. The December event clocked in at magnitude 23, a reading that would translate to magnitude 11 on Earth, enough to split continents. Yet the real terror lies in proximity. Had SGR 1806-20 been within 10 light-years instead of 50,000, the burst would have stripped Earth's ozone layer, triggering mass extinctions. Astronomers estimate such lethal flares hit our galaxy every few million years, meaning ancient Earth may have suffered sterilizing blasts from nearby magnetas. Even today, the magneta SGR 0526-66 in the Large Magellanic Cloud remains a potential threat, its outbursts visible to the naked eye across intergalactic space. What's fascinating is how these events help us map the invisible. The 2004 flare's ionization of Earth's atmosphere created a temporary mirror for radio waves, allowing scientists to study atmospheric layers normally too faint to detect. Meanwhile, the gamma rays themselves carried encoded information about the magneta's crustal composition, revealing it to be a crystalline lattice of iron nuclei floating in a neutron superfluid, matter so dense a sugar cube's worth would outweigh Mount Everest. So while magneta flares might seem like distant curiosities, they're actually cosmic alarm clocks, reminders that the universe isn't just vast but violently dynamic. Their light-speed tantrums connect galaxies across incomprehensible distances, proving that even the most exotic objects can reach out and touch us in ways we're only beginning to understand. Here's something that will bend your mind: entire galaxies are speeding away from us faster than light itself. not because they're moving through space at impossible velocities, but because the fabric of the universe is stretching beneath their feet, carrying them along like raisins in an expanding loaf of bread. This isn't science fiction, it's the reality of cosmic inflation, where the rules of relativity get rewritten on the grandest scales imaginable. Take a galaxy like GNZ11, one of the farthest objects we've ever observed. Its light has traveled 13.4 billion years to reach us, but here's the kicker: because space itself has expanded during that time, the galaxy is now about 32 billion light-years away. That means it's receding from us at speeds exceeding light speed, not because the galaxy is moving through space, but because the space between us is growing. Think of it like two ants on opposite ends of a stretching rubber band. Neither ant is running, but the distance between them grows faster than either could crawl. This doesn't break Einstein's rule that nothing can outpace light. Relativity only forbids objects from moving through space faster than light. It says nothing about space itself stretching. It's the ultimate cosmic loophole, allowing the universe to expand at rates that would make even the fastest pulsar seem sluggish. The proof is written in the light from these galaxies stretched into longer, redder wavelengths by their headlong flight, a phenomenon we call redshift. The farther away a galaxy is, the faster it appears to recede, and the more extreme its redshift becomes. But the real shocker is how this acceleration isn't just happening, it's increasing. Dark energy, that mysterious force driving the expansion, seems to be winning its tug of war against gravity, pushing galaxies apart at ever-growing speeds. Some estimates suggest that in about 150 billion years, every galaxy beyond our local group will have redshifted so far that their light will be undetectable, leaving future astronomers with a night sky devoid of external galaxies. The universe won't just be expanding, it'll be erasing its own history, one redshifted photon at a time. What's wild is that we can still see these ultra-distant galaxies at all. Their light left when the universe was young and space was more compressed, allowing photons to begin their journey toward us before expansion could carry their sources away forever. Every ultra-redshifted galaxy we spot is like a message in a bottle, tossed into an ocean that's growing vaster by the second. And with each new discovery at the edge of the observable universe, we're not just learning about distant corners of space, we're glimpsing the fate of the cosmos itself. So while the speed of light may still reign supreme in the realm of motion through space, the expansion of the universe plays by different rules that let galaxies vanish over the horizon of visibility, not with a bang, but with a redshift so profound it becomes silence. It's a reminder that the universe's fastest-moving objects aren't always the ones you can see sometimes. They're the ones slipping away, carried into darkness by the relentless stretching of space itself. Humanity's fastest spacecraft might seem sluggish compared to cosmic speed demons, but the Parker Solar Probe's 700,000 kilometers per hour still represents a monumental achievement, one that required defying engineering nightmares to kiss the sun's fiery atmosphere. This car-sized spacecraft doesn't just orbit the sun. It dives through its corona, enduring temperatures hot enough to melt steel while relying on a heat shield no thicker than a phone book. The secret, a carbon composite shield that reflects 97% of incoming heat, leaving the probe's instruments basking in a temperate 30 degrees Celsius despite facing 1400-degree plasma. What makes Parker's speed remarkable isn't just the number, it's how it gets there. Unlike cosmic objects propelled by black holes or supernova, Parker relies on meticulous gravity assists from Venus, swinging past the planet 7 times to shed orbital energy and spiral ever closer to the sun. Each pass acts like a cosmic slingshot, incrementally accelerating the probe until it's traveling fast enough to circle Earth's equator in under 3 minutes. At closest approach, Parker becomes the fastest human-made object in history, eclipsing even the Helios probes of the 1970s. Yet for all its engineering brilliance, Parker's speed pales against nature's extremes. The Parker Solar Probe would take nearly 2 weeks to cross the distance that hypervelocity stars like US 708 cover in a single day. Even the "oh my god" particle, a lone proton from deep space, carries more kinetic energy at 99.9% light speed than Parker could muster in a million sun dives. That humbling contrast reveals the universe's true scale. Our most daring missions are still bound by the same Newtonian physics that cosmic phenomena casually defy. The probe's real triumph lies in its endurance. During each solar encounter, Parker's heat shield faces bombardment not just from radiation, but from hypervelocity dust particles striking at over 600,000 kilometers per hour, speed so intense impacts vaporize the dust and part of the shield itself, creating tiny plasma explosions. To survive, Parker's sensors peer around the shield's edge like a sprinter glancing sideways mid-race, collecting data on solar wind and magnetic fields while moving fast enough to outrun any earthly projectile. Future missions might push closer still. NASA, a conceptual solar cruiser, could potentially reach even higher speeds using solar sails. But for now, Parker remains humanity's fastest handshake with a star, proving that even our most blistering speeds are just whispers in the universe's roaring symphony of motion. Imagine a star venturing too close to a black hole, only to be stretched into a brilliant ribbon of plasma before being torn apart in a cataclysmic flash. This isn't science fiction, it's a tidal disruption event, one of the universe's most violent spectacles. When gravity's grip becomes too extreme, stars don't just die quietly, they're shredded into spiraling debris, some of it flung outward at a staggering 10% the speed of light. That's fast enough to cross the entire Earth in under 2 seconds, leaving behind a glowing trail of stellar guts and a black hole feasting on the remains. Take Assassin 14 Lie, the cosmic murder that captivated astronomers in 2014. Located 290 million light-years away in the constellation Pegasus, this tidal disruption event offered the clearest view yet of a star's final moments. As the black hole weighing several million suns ripped the star apart, telescopes caught the aftermath in astonishing detail. The star's outer layers were stretched into a swirling disk of superheated gas, glowing fiercely in X-rays as temperatures soared to millions of degrees. Meanwhile, the innermost debris vanished past the event horizon, but not before launching twin jets of plasma at relativistic speeds, nature's way of marking a stellar crime scene with high-speed evidence. What makes these events so mesmerizing isn't just the destruction, but the physics behind the debris' incredible velocity. The black hole's tidal forces don't just tear the star evenly, they create an uneven gravitational tug, stretching it into a spaghetti-like strand. Some of this material falls inward, but the rest gets whipped around the black hole like a slingshot, gaining so much energy it's ejected at speeds approaching 30,000 kilometers per second. That's fast enough to cross the distance between Earth and Neptune in under 5 hours, a velocity typically reserved for subatomic particles, not chunks of a star. The aftermath of Assassin 14 Lie was just as revealing as the initial explosion. For months, telescopes watched as the black hole's accretion disk flared and faded, its light curve revealing the star's composition like a cosmic autopsy. Surprisingly, the debris contained heavier elements like nitrogen and carbon, clues suggesting the victim was a red giant, its outer layers already puffed up before the black hole's gravity finished the job. Even more astonishing was the discovery of a delayed X-ray echo, caused by light bouncing off debris clouds moving at different speeds, giving astronomers a 3D map of the explosion's chaotic aftermath. But here's the twist, these events aren't just about annihilation. The debris ejected at such extreme speeds carries heavy elements forged in the star's core, scattering them across interstellar space. Over millions of years, this material becomes part of new stars and planets' stellar death, fueling cosmic rebirth. In a way, tidal disruption events are the universe's most grotesque recycling program, turning entire stars into high-speed projectiles that seed future generations of celestial objects. So while Assassin 14 Lie might seem like a tragedy, it's also a reminder of the universe's relentless creativity, where even destruction serves a purpose, and the fastest-moving debris might one day help build something new. Every tidal disruption event isn't just a star's end. It's a fleeting, violent masterpiece written in light and speed. Dark energy isn't just expanding the universe, it's pressing down the cosmic gas pedal, accelerating galaxies apart at speeds that grow faster with every passing moment. This isn't like the steady push of a rocket, it's more like rolling a boulder downhill where gravity should slow the expansion over time. Instead, galaxies are fleeing from one another faster today than they were billions of years ago, as if space itself has a hidden engine revving beneath its surface. The discovery of this phenomenon was so revolutionary, it earned scientists the Nobel Prize in 2011, not for solving the mystery, but for proving the universe is playing by rules we don't yet understand. The breakthrough came from studying distant supernovas, the explosive deaths of white dwarf stars. Astronomers expected these standard candles to reveal how much the universe's expansion had slowed since the Big Bang. Instead, they found the opposite. Supernovas billions of light-years away were dimmer than predicted, meaning they were farther away than they should have been. The only explanation: space wasn't just expanding, the rate of expansion was speeding up. Imagine tossing a ball in the air, only to watch it shoot upward faster as it climbed. That's the counterintuitive reality dark energy imposed on the cosmos. What makes dark energy so baffling is its apparent uniformity. Unlike matter, which clumps into galaxies and stars, dark energy seems perfectly smooth, exerting the same repulsive force in the emptiest voids as it does in crowded galactic clusters. One leading theory suggests it's the cosmological constant, an intrinsic energy woven into space itself, first proposed by Einstein as a fudge factor before being discarded. If true, every cubic centimeter of vacuum, from the void between galaxies to the empty space inside your body, contains a tiny, immutable dose of this repulsive energy, relentlessly stretching space-time apart. But dark energy's dominance wasn't always assured. For the universe's first 9 billion years, gravity held the upper hand, slowing expansion as matter clustered together. Only around 5 billion years ago did dark energies push overwhelm gravity's pull, marking the start of the accelerating era we now inhabit. Future projections paint an eerie picture. In another 100 billion years, all galaxies beyond our local group will vanish beyond an unreachable horizon, their light stretched to wavelengths too long to detect. The universe won't just expand, it will erase its own history, leaving future civilizations with a sky nearly empty of galaxies. Yet for all its strangeness, dark energy's effects are measurable in subtle ways. The large-scale structure of the universe, the cosmic web of galaxies and voids, bears its fingerprint in the spacing between clusters. Even the rate at which galaxies spin, influenced by the expanding space between them, offers clues. Current telescopes like the Dark Energy Survey and future missions like Euclid are mapping these patterns with unprecedented precision, hoping to distinguish whether dark energy is truly constant or varies over time, a distinction that could upend our understanding of physics. The most unsettling possibility: dark energy might not be the final answer at all. Some theories suggest it's a sign of new physics beyond Einstein's relativity, perhaps tied to extra dimensions or quantum gravity. Others propose it's an illusion caused by our imperfect understanding of gravity on cosmic scales. What's certain is that this mysterious force isn't just a footnote in cosmology. It's the dominant actor in the universe's unfolding story, silently shaping the fate of everything we see. And as galaxies race apart faster than light can bridge the gaps, dark energy ensures the cosmos will always keep its deepest secrets just out of reach. Imagine a spacecraft so light and fast it could reach our nearest star system in just 20 years, not centuries. That's the audacious vision of Breakthrough Starshot, a plan to send gram-sized probes to Alpha Centauri riding nothing but laser beams. These aren't your grandfather's rockets, they're starships, wafer-thin spacecraft equipped with cameras and sensors, attached to sails thinner than a human hair. When a ground-based laser array stretching kilometers across fires a 100-gigawatt burst at these sails, the push would accelerate them to 20% light speed in mere minutes. At that velocity, crossing the 4.37 light-years to Alpha Centauri would take about 20 years, with another 4+ years for the data to ping back to Earth. It's the closest thing to a starship humanity has ever designed, and it relies on physics we already understand, just scaled to extremes. But speed like this comes with astronomical challenges. At 60,000 kilometers per second, even a speck of interstellar dust becomes a deadly bullet. A grain weighing mere micrograms would strike a Starshot probe with the energy of a hand grenade, enough to vaporize it instantly. Space isn't empty between stars. There's about 1 dust particle per cubic centimeter. That might sound sparse, but at relativistic speeds, it's like running through a hailstorm. The probes would need some combination of shielding, evasion, and redundancy to survive. One proposal involves coating the leading edge with beryllium copper, an ultra-tough alloy that could vaporize incoming particles before they penetrate. Another suggests spreading the probes into a swarm to increase the odds some survive the journey. Even then, engineers estimate each probe might have only a 50% chance of reaching Alpha Centauri intact, which is why Starshot plans to launch thousands. Then there's the problem of steering. A laser push only works in one direction once the probes are en route. There's no slowing down or course correction. They'd whiz through the Alpha Centauri system in mere hours, relying on AI to pick targets and snap images autonomously. The sail itself could double as a communications antenna, using its phased array to beam day to home via a 1-watt laser, a signal so faint it would require football field-sized telescopes on Earth to detect. Every aspect pushes the limits of technology. The lasers must stay perfectly focused over thousands of kilometers of atmosphere. The sails must reflect 99.99% of light to avoid melting, and the probes must survive decades in the deep cold of interstellar space. Yet if it works, the payoff would redefine humanity's place in the cosmos. Starshot's flyby probes could capture the first close-up images of exoplanets like Proxima Centauri b, scanning for oceans, continents, or even signs of artificial light. They'd measure magnetic fields, analyze stellar winds, and map the system's dust belts data that could reveal whether these worlds are barren rocks or potential havens for life. More fundamentally, Starshot would prove that interstellar travel isn't just for sci-fi, that with enough ingenuity, even a civilization confined to one planet can reach for the stars. The project's timeline is as ambitious as its engineering. Prototypes in the 2030s, a launch by the 2040s, and the first interstellar postcards arriving by the 2060s. Along the way, Starshot would spin off technologies with earthly uses, advanced lasers for clean energy, lightweight nanomaterials, and AI capable of navigating the unknown. Some critics call it a billionaire's pipe dream, but its architects argue that every epochal journey begins with an impossible idea. After all, the same was once said of the moon landing. Whether Starshot succeeds or fails, it's already rekindled an essential truth. The universe belongs to those who dare to move fast. Most stars spin gracefully, like dancers twirling in slow motion, but VFTS 102 is the universe's ultimate breakdancer, whirling so fast it's nearly tearing itself apart. Clocked at a mind-numbing 2 million kilometers per hour, this hypervelocity star doesn't just rotate, it flirts with cosmic catastrophe, stretching into an oblate shape as centrifugal force battles gravity in a tug of war at the edge of physics. For context, that's 600 kilometers every second, fast enough to cross the continental United States in under 7 seconds, or circle Earth's equator in just over a minute. If our sun spun this fast, it would complete a full rotation in under 15 minutes instead of 25 days, its equator bulging outward until the star resembled a glowing cosmic pumpkin. What's truly staggering is how close VFTS 102 is to its breaking point. Every massive star has a critical velocity, the speed where rotation overpowers gravity, flinging its outer layers into space. VFTS 102 spins at 96% of this limit, meaning its surface material is barely clinging on, held only by the star's immense gravity. Spectroscopic measurements reveal its equator whips around so fast that hydrogen gas is nearly being slung off into space, creating a hazy corona of barely contained starlight. This isn't just fast, it's a stellar tightrope walk where one extra nudge could trigger an explosive disintegration. The secret behind this dizzying spin lies in VFTS 102's violent past. Astronomers believe it was once part of a binary system orbiting a neutron star or black hole companion. When that companion went supernova, the asymmetric explosion acted like a cosmic slingshot, ejecting VFTS 102 while simultaneously transferring enough angular momentum to send it spinning into overdrive. Now alone in the Tarantula Nebula, the star's rapid rotation has sculpted its atmosphere into dramatic temperature bands, scorching hot at the poles where centrifugal forces compress material, and slightly cooler at the bulging equator where gases stretch thin. Even its light is distorted, appearing brighter when the bulging side faces Earth due to relativistic Doppler beaming. But VFTS 102 isn't just a cosmic oddity, it's a preview of stellar extremes. Some models suggest such ultra-rotators might eventually evolve into collapsars, their cores collapsing so rapidly into black holes that the outer layers form gamma-ray burst jets. Others speculate they could shed their outer layers entirely, leaving behind rapidly spinning stellar skeletons called quark stars. Every high-speed wobble of VFTS 102 is a clue to these mysterious processes, a real-time experiment in how matter behaves when pushed to its rotational limits. So while it may look like a star on the verge of flying apart, it's actually something far more valuable, a laboratory for the universe's most extreme physics, spinning at speeds that rewrite the rules of celestial mechanics. At the farthest edge of physics lies a phenomenon so bizarre, it made Einstein himself call it spooky action at a distance, a quantum entanglement, where particles can instantaneously influence each other regardless of separation. Picture two coins flipped in opposite corners of the universe that always land matching heads with heads, tails with tails, even though neither coin has a predetermined outcome until observed. This isn't hypothetical. Experiments have confirmed entangled particles coordinating their states faster than light could travel between them, seemingly breaking cosmic speed limits. But here's the catch that preserves relativity. This coordination can't transmit information. Imagine those quantum coins only ever show matching faces, but you can't force them to land heads or tails. Observing one instantly sets its partner's state, but you have no control over what either reveals. It's like having twin magic 8 balls that always give identical answers. You can't choose the response, only witness the synchronization. Without the ability to dictate the outcome, no meaningful message can be sent, leaving light's speed unchallenged as the universe's ultimate communications cap. The mechanism behind this remains physics' greatest magic trick. When particles entangle, their quantum states become interdependent, described by a single mathematical wave function. Measuring one collapses the entire system instantaneously, like cutting a tether connecting two buoys. The distant one doesn't feel the cut through space. The connection simply ceases everywhere at once. Recent experiments with entangled photons separated by over 1,200 kilometers have clocked the coordination happening at least 10,000 times faster than light could cross that gap. if it even makes sense to call it speed when no actual movement occurs. What makes entanglement truly revolutionary isn't the illusion of speed, but how it reshapes our concept of reality. The universe at its fundamental level doesn't play by classical rules of separate, localized objects. Entanglement suggests everything is interconnected in ways that defy traditional notions of distance and individuality, an insight already fueling quantum computing breakthroughs. So while we can't exploit this phenomenon for faster-than-light messages, it remains nature's ultimate demonstration that the cosmos operates on principles far stranger than fiction, where the fastest connections aren't through space but beneath it. From the unbreakable cosmic speed limit of light to the cataclysmic particle jets of gamma-ray bursts, the universe never ceases to astonish with its extremes. Let's revisit the top 5 most breathtaking velocities we've encountered, starting with light itself, the universe's ultimate speed demon. At 299,792 kilometers per second, light doesn't just move, it defines motion, bending time and space to its will while remaining forever out of reach for anything with mass. Then there are gamma-ray bursts, nature's most violent particle accelerators, flinging matter at 99.999% light speed, so close to the limit that time itself distorts in their jets. Not to be outdone, hypervelocity stars like US 708 race through the void at 1,200 kilometers per second, flung from their galaxies by supermassive black holes in gravitational slingshot maneuvers of cosmic proportions. But speed isn't just about brute force, it's also about precision. Take pulsars, the lighthouses of the cosmos, spinning hundreds of times per second while shooting beams of radiation across space with clockwork regularity. And who could forget dark matter, invisible yet omnipresent, its halos whirling around galaxies at 220 kilometers per second, holding the universe together with gravity's unseen hand. Each of these record holders reveals a different facet of velocity's role in shaping the cosmos, from the delicate balance of galactic rotation to the raw power of relativistic jets carving paths through interstellar gas. Yet for all we've uncovered, the universe always keeps its fastest secrets just out of reach. What undiscovered phenomena lurk in the voids between galaxies or deep within black holes, where physics as we know it breaks down? Could quantum entanglement's spooky action hint at speeds beyond light, or will dark energy's accelerating push forever keep the cosmos's true nature hidden? The frontier of cosmic velocity is far from settled. Every discovery peels back another layer, revealing new questions as thrilling as the answers. So now it's your turn. Which of these cosmic speed demons left you awestruck? Was it the rogue star fleeing its galaxy, or the gamma ray burst brighter than 1,000,000 suns? Drop your favorite fact in the comments, or tell us what mysteries you'd explore in part 2, because in a universe this wild, the next revelation might be just one observation away. Until then, keep looking up. You never know what might come racing into view.